Hi, we've been talking about conceptual design, and now we're going to talk about moving from the concept creation to doing some of the preliminary engineering analysis that turns it into an engineering concept. After the divergent conceptual thinking, we have to converge on design ideas that might be feasible and then assess them according to some technical criteria so that we can decide which concept to take into detailed design. An application usually considers timeliness, quality, and cost. And with care, we can get maybe two of these. Quality means, well, whatever the client thinks it means. It might mean the performance of its functions, it might mean its aesthetics, it might mean its durability, or some combination. Today we're going to consider performance. Performance criteria are descriptions of product function expressed quantifiably using mathematical physics. This predictive capability during design separates engineering from mere invention. There are three types of system behavior that we can analyze: equilibrium, or steady state; eigenvalue, that is critical load conditions such as oscillations or buckling; or dynamic time-varying behavior, that is a transient time-varying load that's causing the system to behave, driven by that load. Once we've decided how the system is likely to behave, then we have two choices on how to model these physical systems: as a continuous system or as a lumped parameter system, with a set of distinct elements that each has its own specific physical characteristics. In a continuous formulation, the system is modeled by deriving differential equations that represent the physics of the continuous system, such as a beam with stress-strain relationships, for example. The solution to the differential equations requires that they be approximated by algebraic expressions, such as finite difference equations, for almost all non-trivial cases. The properties of the continuous system can instead be visualized as being separate from one another. A beam could be modeled as a linkage mechanism with a set of rigid links connected by springs, deflecting under an external load. Then we find a set of algebraic equations from which we can determine the deflections, or even a set of differential equations if the links have mass. More generally, lumped parameter systems can be modeled using generalizations of Kirchhoff's laws to formulate governing equations for a range of different kinds of physical systems. The price we pay is one of approximating the physical system at the modeling level, enabled to generate governing equations that we can solve. So both types of systems require some modeling simplification to be able to generate a set of equations that can be solved. But once the model's been developed, then numerical procedures can be used to study system behavior, usually using computers. These approaches to creating an understanding of how a system will perform can be done for mechanical, electrical, fluid, thermal, and even combined systems. Usually in the preliminary evaluation of a conceptual design, we start by picking some steady-state case, which makes the equation simpler to formulate rather than dynamic cases. For example, power to attain a speed with some approximate drag, or the total requirement of energy or mass that's needed to achieve some task under constant conditions. Next time, we'll discuss more specifics of the kind of calculations that we might do to assess performance at the conceptual stage, as well as system durability and reliability.